Hello and welcome back to yet another math video. In this video, I'll be going over the properties of logarithms, and more specifically, how to condense, expand logs, and how to use the change of base to approximate logs that aren't a common or natural base. Let's get into it. Before I get to condensing and expanding, I've got to go over the product rule for logs, the quotient rule for logs, and the power rule for logs. So very briefly, product rule states if you have two logs with the same base being added together, you can condense them into one log with that same base, and you multiply the arguments together. The arguments are what's on the inside. So something similar with quotient rule. If you have two logs with the same base, and one log is being subtracted from another, then you can divide the arguments. Note here, the log with the positive sign in front of it, the argument of that log will go in the numerator, and the argument of the log with the negative sign in front of it will go in the denominator. The last one here, power rule. Power rule states if your log has a coefficient, you can move it up into the exponent of the argument. And just to give this some context, it would be inside the log. And you have to use the power rule to move an exponent to condense, right? We have to move the exponent or the coefficient into the exponent before you can use the product or quotient rules, because you'll notice that none of these logs have a coefficient in front of them. The last thing I want to say is I've already made use of the word condense. If you start on the left of any of these equations and you work your way to the right, that is the condensing step. And since condensing and expanding are opposites, the expanding steps would end on the left and start on the right. So expanding means you take one log and turn it into many logs. You can see it here. Or you're taking an exponent that's inside of a log and pushing it to be the coefficient of that log. Whereas condensing takes many logs and turns it into a single log. Or takes a coefficient and turns it back into an exponent. All right, on this slide and the next slide, I'm going to attempt to explain why the log rules work. So up here, we have a log base b of m equaling x and a log base b of a equaling y. So I'm going to make a very brief rewrite here. If you rewrite this in exponential form, you get b to the x power equals m. And if you write this in exponential form, you get b to the y power equals a. And that'll be important here in just a little bit. So we have the starting point here, log base b of ma. And what I'm going to do is I'm just going to make a substitution. You can see that m is equal to b to the x power. So I'm going to write b to the x power. And there's a multiplication in here between m and a. And a over here, you can see, is equal to b to the y power. All right, from here, we can combine these two bases. Since they're like bases, we can add the exponents together. So it'll be b to the x plus y plus y. There we go. And then we can actually reduce this log to be just x plus y. If the base of the log matches the base of the argument, the answer is just the exponent. There you go. From there, I'm just going to substitute back. Up here, you can see x is equal to log base b of m. So I make that substitution, and y is equal to log base b of a. Make that substitution. So what this string of equalities shows us is that the log base b of m times a is equal to log base b of m plus log base b of a. On this slide, I'm going to jump to why the power rule works and not show why the quotient rule works, because the quotient rule is very similarly proven like the product rule on the last slide. So let's start. I'm going to have this nice little equation here that the log base b of m equals x. And I'm also going to make sure that everyone out there understands that if you rewrite this in exponential form, the base will get the exponent. Again, the log is always equal to the exponent. So b to the x power will equal the argument, the insides. All right, so in this example, we have to start with log base b of m to the p power, and we're basically going to come over here and we're going to prove that this equals p times log base b of m. How do you do that? Well, we're just going to make a couple substitutions and maybe a couple simplifications. M is the same thing as b to the x power. So if I replace m with b to the x power raised to the p power, that's what's inside now. Now we have a log base b of b to the xp power. We can multiply these two exponents together. And like in the last example, if the base of the log matches the base of the argument, the answer is just the exponent. So I've got, let's see, xp over here. And then you can see where p ends up. And then x is the same thing as log base b of m. So x and p sort of switch positions here, and that's fine. You're allowed to do that with multiplication. And there you have it. So we basically have now proved that this is equal to this. With those little proofs out of the way, it is time to now learn how to condense logs. So the first thing you want to do when you're doing this, as I mentioned in the rules slide, you have to move the exponents up before you can do anything else. Once you move the exponents up, you can then use the product and quotient rules more or less all at once to combine the logs into a single log. Then in some cases, you may have to repeat steps 1 and 2. And that's fine. And then once you finally get every log simplified into one log, you can see if anything reduces. So let's take a look at this first example down here. So, yep, we have to first see if there are any coefficients, and they're here. Here's one. So when I say we move the coefficient up into the exponent or move the exponent up, what I mean is we're going to write log x minus 5, log of x minus 5 minus. So this sign will not change. What we can do is just move the 2 up into the exponent. So this would be log of 3x squared. There we go. From here, since there are no coefficients in front of these logs now, we can combine them into a single log. And that would look like, let's see, subtraction would mean you use the quotient rule. So we would have log of x minus 5, and the x minus 5 would go in the numerator because that log that contained that is positive. the log that contains 3x, the quantity squared, is negative, so that will end up in the denominator. That's it. For the other example over here on the right side, we have a coefficient again. It's 6. Okay, and the first thing we need to do is move that to be the exponent. And so what do we get? Log base 2 of x plus 1 to the 6th power plus log base 2 of 4x. All right, so you take a look at the logs across the board. There's no coefficient here. There's no coefficient here. Great. So what we can do then, since we're using plus, we have an addition between these two logs, we can just combine these using the product rule. So this would be log base 2 of x plus 1 to the 6th power times 4x, and we're done. And on this slide, the doozy. So there's a lot to unpack here. You see there's a coefficient that is being multiplied to all the logs. And even here, there's a coefficient being multiplied to these two logs. Let's see, there's a coefficient here already. So I think the best way to attack something like this is to first, we can distribute the two. So we get this. All right, from here, because I see a fraction that is I guess, needs to be distributed to all of these logs, I don't want to do that because then I'll have fractions here, 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 here. I don't want that. So what I'm going to do instead is I'm going to condense everything inside this bracket. And yeah, you're allowed to do that. So what that would look like, we can't condense until we move exponents. I'm going to move this exponent up here, or coefficients to become exponents, I guess. And remember, you're just moving the number. Don't worry about the signs. We'll take care of the signs in the next step. Okay, all of the exponents have been moved up. Let's see. Then we can combine this all into a single log. Check out how this works. This will be 1/6 natural log. All I'm going to do is write one fraction right now, like this. There we go. So what I'll do is I will take any argument that is inside a positive log, right here, and I'm going to put it in the top. Well, how are you supposed to put them in the top? Well, you just write them up there. This is x plus 9. And since we're adding all of these together, all of these logs together, this will mean that we multiply them when we put them into the single log. We multiply them when we condense. And what's really cool about this is the same thing happens with all of these arguments inside the negative logs. We can just put all of these arguments into the denominator and make sure they're all multiplied together. So this would be x cubed, x plus 1 squared, minus, oh, not minus, x squared minus 81. Okay, there is the new log. And even before I move the 1/6 up to the exponent of this entire thing, I want to see if anything here will reduce. I may as well do it now before we start dealing with this fraction. So if you look here, this x squared minus 81, that factors. And in fact, it factors into x plus 9 times x minus 9, which means you have a factor of x plus 9 in the denominator, and you have a factor of x plus 9 in the numerator, and that means they reduce away. So now I have a natural log of all of this stuff. X minus 5 squared, x cubed, x plus 1 squared, and x minus 9. And you say, oh man, you forgot the 1/6. Well, at the same time I clean up this in the argument of this log, I'm going to move that 1/6 up into the exponent. And you're done. Moving on to expanding. Expanding is the opposite, aka inverse, of condensing. And when you expand, as you can see in these two examples here, you'll want to write a single log as many logs being either added or subtracted. So that's what we'll do in the first step, expand. In the second step, we will move the exponents down, and then we may have to go back and expand again and move more exponents down and repeat these, kind of like in the condensing process. But from there, at the very end, we need to simplify. And it really just depends on what you start with as to which step you need to start with here. So for these two examples, you'll see we've got to start with expand. But on the next slide, the next example, we're going to have to move exponents down first. All right, let's take a look at this one. So when we were condensing, we said any base that you see in the numerator of a fraction inside of a log will go inside a positive log, and anything from the denominator will go inside a negative log. So when you write this out, when you expand this out, you'll get log base b of x squared. You'll have a second log base b of y, and you'll have a third log base b of z to the third power. As far as the signs for these logs, the first two will have plus signs, like I just mentioned. The last log with z will have a minus sign in front of it because that base was in the denominator of this log. So that is the expand step. The very last step here is to move the exponents down to the front. So 2 log base b of x plus log base b of y minus 3 log base b of z. There's the answer. For this next example, the log of the square root of x over the ninth root of y to the fourth, what you'll have to remember is how to rewrite radical notation into exponential notation. So off to the side here, I have a nice little rule that we can remember. Whatever root you're taking, the b root, and whatever exponent the base has, the t exponent, we can rewrite something like this as a to the t over b power. Notice the exponent here went in the top, and the root here went in the bottom. And then these two expressions are equivalent. So it doesn't matter if that exponent is inside the root or the entire root is being raised to an exponent. You can write it like this. So what does that mean? Well, in a radical without any root number given, it's going to be 2. The square root is always 2. And the exponent, if there's no exponent, it's 1. It's understood that it is 1. So this brings up something that's a little more general, or a little more specific, I should say, is that when you have a square root, that is the same thing as raising something to the 1/2 power. And that shows up very frequently in successive math courses. So to a lesser extent, knowing this helps out a lot. But 1/2 being 1/2 exponent being square root shows up a bunch. All right. So to finish out this exercise, this would be log of x to the 1/2 power over y to the 4/9 power. There we go. You can separate this out. Log x to the 1/2 log y to the 4/9, and the log with the x argument will be positive because it came out of the numerator of this fraction, and the log with the y to the 4/9 will be negative because it came out of the log, or it came out of the denominator of that log. And then the last thing that needs to happen here is we just move those exponents to the front. And here's the answer for the second example. All right, on this slide, the expanding doozy. So we had a doozy of an example when we were condensing, and now we're expanding everything. So how does this work? On the last slide, I said you kind of have to gauge, depending upon what you're looking at, where you need to start. And I know in this particular example, I'm going to have to start with moving an exponent down. And that's because this entire expression in here is all inside this radical. All right. So what I need to do first is I need to rewrite this log in this following manner so that everything here is being raised to the 1/6 power. And what I'll do is I will bring that to the front. And then we can start expanding logs. All right, so with the product and quotient rules now, I'm going to expand this out. And I hear a lot of you out there, but hey, you can't. You said if you have a coefficient in front of your log, you cannot expand or condense logs together. Okay, so here's what we do. Here's how we handle this situation. This 1/6 is being multiplied to this log. So what we can do is we can look at the 1/6 and the natural log as separate factors. And if you look inside this set of brackets, there is no coefficient here being multiplied to the natural log. But what that means is this 1/6 will come down to the next step. It'll still be 1/6 times some expansion that we will have for this log. Now, as we try to expand this log out, you need to take note as to how many different logs there will be when you expand it out. What do I mean by that? You look in the last couple examples, it was pretty easy to tell the different bases that were in the argument. We had x's, y's, and z's. But when you start throwing coefficients into the mix, it can start becoming a little more confusing. So here, I see an x being raised to the second power. And mind you, this square only affects the x, it does not affect the 2. So we've got x squared, so I'm at least going to write that. So I've got a natural log of x squared. That's this piece right here. I've got a plus a natural log of the square root. Oh, maybe I can just write it like this. X squared plus 1 to the 1/2 power. Because remember, a square root is the same thing as a 1/2 power. In the denominator, so I'm going to subtract now. I have a natural log of, we have this thing to the 5th power. So natural log of x plus 1 to the 5th power. So I'm done with that. Oh, we have something else being raised to a power, so e to the 13th, so minus natural log of e to the 13th. Okay. But you'll notice that after I did all of these natural logs expanding here, there's still a 2 and a 5 that I have not taken care of. 2 and 5 each get their own separate logs. So here we would have a plus natural log of 2 and a minus natural log of 5. So if you have any coefficients either in the numerator or denominator of the argument of a log, those coefficients are going to get their own logs when you expand it out. Okay, from here, we can bring exponents to the front, like this. Let's see. I've only got room for one more step here, so what I'm going to do is I'm going to have to do a couple steps at once. One of the final steps that we're going to have to do is distribute this 1/6 to everything and simplify fractions if we need to. The other thing we need to do is be on the lookout for simplifications. And generally, the only simplifications are going to happen when you have a base of the log. Remember, the natural log base is e. All of these down here have a base e. If the base of the log and the base of the argument are the same. So that means I'm looking for anything in parentheses that is an e. Oh yeah, here. So this natural log has a base e. The argument inside has a base e. The exponent here is 1. It's e to the 1st power. So this log here equals 1. 13 times 1, or rather negative 13 times 1 is negative 13. So this entire term here is just equal to negative 13. From there, we can multiply 1/6 to every coefficient in front of every log, or just if there's a constant, that's fine. And here's what you'll get. There it is in all its glory. So the 1/6 times 2, you would have to multiply the 2 into the numerator, so 2 over 6 is 1/3. Here, 1/2 times 1/6, multiply the numerators together, 1 times 1 is 1. Denominators, multiply those together, 6 times 2 is 12. And so on and so forth and fine. And just as a quick reminder, I know I just said it, but natural log of e is 1. 1 times negative 13 is negative 13. And then when you multiply negative 13 by 1 over 6, you'll get minus 13 over 6. I just wanted to make that clear again. All right, one last topic. Last slide, change of base formula. Now normally what'll happen is on a given calculator, you'll have logs, 2 different log buttons. You'll have log, which is implied to be base 10, or you'll have ln, which is implied to be base e. But you'll notice that, at least even in this video, that there are other possible bases that a log can be. And these two are the most common, so we tend to work with common logs and natural logs. So when we get one of these oddball bases, basically anything that's not 10 or e, we need a way to be able to understand what it's telling us. So what we do is we have this change of base formula. The change of base formula says we can change a log with any base into logs with base 10, aka common logs again, or natural logs. And you can use whichever one you feel like using, but I say once you pick one, stick with it. So log base b of a, where b is not equal to 10 or e, we can rewrite it as a ratio of two logs, log of a over log of b. So this one will go in the top. The argument will go in the top. And as one of my coworkers says, the base will go in the basement. So you can either use common logs, which again is something that you can find on a given calculator, or you can use natural logs. Again, a natural log of a going in the top, natural log of b going in the basement, the base in the basement. And there are just a couple quick examples here to explain how that works. For example, in this first one that we have here, we have log of base 0.75 of 32. We would say the log of the argument all over the log of the base. And you can approximately figure that out on any calculator to be negative 12.0471. And for whatever reason, most of the time when you're trying to figure out decimal approximations involving logs, you'll have to use 4 decimal places. So that's why I went out 4 decimal places here. For this other one, I'll go ahead and use natural log notation just so you can see it. So in this example, it would be natural log of the argument over the natural log of the base. And then you can see that this will approximately be 4.2362. Again, to 4 decimal places. And you can go through yourself to see if you get the same answer if you use natural logs over here, natural log of 32 divided by natural log of 0.75, or if you use common logs over here, log of 105 divided by log of 3. Now a quick note when you're using the calculator with logs. So when you're typing in a log, or when you're typing, let's say, this example into a calculator, you can hit the log button and it'll pop up with log in an open parenthesis. So you'll hit 32, but before you start dividing, you need to make sure you close your log up. And then you can divide log. You hit the log button again and it'll say log with an open parenthesis. You can type in your number 0.75. Make sure you hit a closing parenthesis, and then you can hit enter or equals or whatever the button is on your calculator that computes things. This concludes the lesson for log properties. I hope this makes sense. I hope you have a better understanding of math now. And as always, good luck.